Alrighty. So we were looking at this, trying to figure out the energy stored in a capacitor. So we looked at potential energy as Q delta V. And then for a tiny change in Q, delta V is essentially constant. And so we get this differential equation that we have to solve. Potential energy in the capacitor. We're going to replace delta V with Q prime over capacitance. And you can pull the 1 over C constant up front. This allows us to use the most fundamental integration identity. That's our power rule. We evaluate from 0 to Q. Oh, let's see, that's going to be 1 over 2C. And then Q prime, so 0 to Q will be Q minus 0. Squared. Squared. So that means that the energy in a capacitor, yeah. So this is another format for the energy stored in a capacitor that you can use. Q squared over 2C. But if we remember, C Q over delta V. So that gives us the other format for energy in a capacitor, 1/2 Q delta V. All right, so we have a large parallel plate capacitor with air between the plates. Why is that important? It's not in a vacuum. We just got done talking about dielectrics. What is the problem telling you air between the plates gets you? So no matter how you set this up, dielectric constant of air is 1. It's kind of like telling you that a particle starts at rest. Okay, they're separated by 1 centimeter. Plate area is 314 square centimeters. The capacitor is connected to a 20 volt battery and then disconnected after charge. How much work is done on the capacitor after as the plate separation is increased to 2 centimeters? So I'm going to help you with the first part. Then I want to see if you know how to use it. So the first thing I want to do is I want to do a ratio of my final energy to my initial energy. Okay. So that's going to be Q squared over 2 final capacitance, or Q squared, to initial capacitance. You can see initial over C final. What's an equation for capacitance that I can use? Because I want to get this in terms of a ratio of differences, or a ratio of separations. Yeah. So remember, C is epsilon 0 A over D. So we have our initial distance. Our final distance. And so that gets us a ratio of the final distance to the initial distance, which is going to be 2 centimeters. 1 centimeter equals 2. So this means that the final energy in the capacitor is going to be 2 UI. Now, take a couple minutes to see if you can figure out the work done as the plate separation increases to 2 centimeters. This is also kind of important if you're looking at design of capacitors. The distance can help dictate how much energy is actually stored in that system. Mhm. It all comes down to your equation for work. No, UI. Does anyone have an answer yet? You should get something in nanojoules. You get stuck. Well, what is the equation for work? And delta K is what? Not one. There is no kinetic energy. Right. So we want the potential energy initial, which will be the potential energy of our capacitor. We have 1/2 Q delta V, but we don't have Q. So we remember that Q is C delta V. And then our capacitance, because we also don't have that. Epsilon 0A over that initial distance. Because I put in for Q, C delta V. So our area, we're going to want that in meters. So you know, 314 square centimeters. That is going to be 1 times 10 to the 4th square centimeters per square meter. So you have your separation, and then your delta V is 20 volts. This will get you 5.56 times 10 to the -9 joules, which is nanojoules. We have to figure out how to eliminate the stuff you don't have. Are you talking like the unit or the? Oh, that is electric potential. The book wanted to keep it separate from potential energy because they're two different quantities, but it's traditional to use V for potential because, of course, the units are in voltage. That's how you make a circuit work. You have to put a constant delta V across the circuit. That's how current flows. Okay, now you're ready to do all the problems at the back of that chapter. Now we're going to be working on electric current and circuits. Now at the beginning, this is pretty straightforward and simple. Make sure you get down the initial stuff because once we start analyzing circuits, you're going to have more to keep track of. You are going to need to remember your capacitance equations. We're going to learn resistance. So just your basic current is an amount of charge passing through a conductor per unit time. So the relationship is delta Q over delta T. So essentially current, it's charge per unit time is kind of the electric equivalent to velocity. You have a new SI unit. What does the A stand for? Huh? Amps, amperes. I don't think there's an accent in that word anywhere. Amperes. And that is 1 amp is 1 coulomb per second. Oh, there'll be more as we go along. You're going to have to get the unit for resistance, which is ohms. And that's usually the symbol that people hate drawing the most. It's a capital omega. Now, the thing that runs circuits is called EMF. So technically, the delta V of your battery or your power source is the EMF. It's called the electromotive force. It is the delta V that will cause the current to flow through the circuit. And as you can see, EMF is always represented with that script E. So if you look in the textbook, they make it all fancy. And so your units for EMF are joules per coulomb because it's charge per unit. So it's energy per unit charge. And we know the joule per coulomb is the what? That's a volt. So your EMF is the voltage that is the voltage from your power source that drives the current in the circuit. So you can have a relationship for work done by an ideal battery, and that's going to be your EMF times Q. Well, yeah, because the whole point is, remember, work has to be in joules. So if we take joules per coulomb times coulombs, we get joules. Now for this one, I want to make sure that we use subscript. The subscript on there is a lowercase b, because capital B will come into play with magnetic fields, and I don't want to use that. I don't want to use that letter too much. So you're going to have to learn how to start drawing circuits. We're going to need some symbols. What's that? Nope, we'll get to that. Actually, when you see switch, you're going to go, oh, that's obvious. That's battery. You could draw all your batteries this way. Technically, this is the single cell battery. Batteries can be any number of these. So like sometimes you'll see a textbook do and you could do more than that because like this is a double cell battery. These are your battery symbols. In particular, this is a DC battery. What is DC? Direct current. What's the difference between direct current and AC? So you have the idea now. So a direct current is always directed in the same way. An alternating current will flip its poles, its plus and minus periodically. See if you can tell me what this one is. Oops. Nope. What does it look like? That's a capacitor. Then we have the symbol that looks kind of like how some of you draw your sigmas. What is that? Just a zigzag line. No, no, it's not that. No, we'll get to that. This is one of the circuit components we haven't dealt with yet. Mhm. What do you think this is? Ohms is for what did we just say? It's some yeah. You said this is your resistor. Now, let's see. Yep. What's that? It's essentially a wire going into a well. What have, what have we called that before? Grounding. This is your grounding symbol. Now this one I'll have to help you with, but I just want to see what you come up with. Because we'll work with this eventually. This has the letter L in your textbook. I think it's L. Nope, not a light bulb. Kind of the same idea, but not a light bulb. It's a wire coil. That's why it looks like this. It's actually a wire coil in your circuit. Nope. It's actually trying to have the opposite effect. Yeah, nope, it's trying to manage the current in the circuit. This is your inductor. Now, Piper, you've tried this one twice. No, no. It's the same thing as a battery. This is your AC symbol. So just like your battery up there was DC, this is AC. Yeah. It's just your standard bat. You'll use this one. But you can draw, if you open a book and you see it drawn out to multiple cells, it's the same thing. You can call it battery. That's it, alternating current, that's your AC. Oh, that's your inductor. So, and you won't have, you can call these both battery. Your circuit will be defined by the symbol that you use. So if you use the top one, it's automatically a DC circuit. If you use the AC symbol, it's automatically an AC circuit. You can call them both. So the way you'll usually write them is you usually write these as your EMF. Because again, the circuit's going to be dictated by the symbol you use. Now, Maddie guessed switch earlier. Let's see why that one is extremely obvious. That's a switch. Actually, that's the same thing in circuitry. So, I mean, Gates can be a little different, but we're not going to get into logic circuits in this class. Okay, so those are the symbols we're going to be working with. Now, you see here a very basic circuit put together. This is an RC circuit. So you can tell the kind of circuits you have by what it's called. You have RC circuits, you have RLC circuits. So here you see a capacitor and a resistor, and we call this in series. The series means one right after the other after the other. That is the direction of your current. Now, pay attention how that's your positive terminal, that's your negative terminal. And the current is going around from positive to negative. Which way do the electrons flow? Electrons flow against the current. So when you're drawing circuits, you're drawing the current from positive to negative, but you realize that electrons go the opposite direction. The sides of your capacitors and resistors and inductors, they're going to line up with the side of the battery they attach to. Okay, so let's start talking about what current is. So you have two diagrams here. The first one is inside of a metallic conductor when no delta V has been applied. Your electrons, do you remember metallic bonding from chemistry? Yeah, so your electrons are essentially like a cloud inside the metal. They're bouncing all over the place. They're bouncing into the positive nuclei of the individual metal atoms. But then if a delta V is applied, you get an electric field through the material. The electrons start moving. So again, notice your electrons move the opposite direction of the electric field. We've been talking about that, how negative charge goes against the electric field, positive charge goes with it. So the electrons are going to start to move that way. But as you notice, they're still bouncing around, they're still hitting things, they still have kind of a randomized pathway based off collisions inside the material, but they still have an overall velocity that direction. That is what we call drift velocity. So I'll ask you the same question that was asked of my undergrad class, and I don't want to hear the same answer that this guy I knew in undergrad gave. So think of it this way. So now you know that electrons have a finite drift velocity inside the material. Why, when you hit the light switch, do the lights come on immediately? Why is there not a delay? What turns on the light? Do the charges have to reach the light? Do they have to hit the circuit? No, what turns on the light? Why can I hold a light bulb in the air and turn it on? Yes, I actually have ways to hold a light bulb in midair and turn it on. Huh? Well, no, but you're getting, what'd you say, Piper? I did, but what is essential in the circuit to, so yeah, I hit the light switch, I close the circuit, lights come on instantaneously, even though there's a finite drift velocity. No, but that's right on the level of what that guy gave in undergrad. His answer was because electrons are super fast, but he put that on an exam. So no, that's not the answer. That's not the answer. The electrons transfer something down the wire. What do they transfer? What is the necessary thing to turn on the equipment? Huh? It's the delta V. The electrons transfer the field down the wire at the speed of light. The electrons are not moving that fast. They transfer the field. And once you close the circuit and the delta V exists, the 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 lights or whatever turn on. So the reason you can hold a light bulb in the air and turn it on is if I have a strong enough Tesla coil, I just hold that light bulb in the delta V produced by the Tesla coil. It turns on. Well, I'm not holding the Tesla coil or I would be dead. So once again, we do not touch Tesla coils. We do not put things in wall sockets. Yeah, because the delta V forces the electrons inside to either move or, in the case of what we call it neon, but it's not always neon gas, but a bulb with gas in it, the delta V will cause the electrons to excite and then resettle, emitting photons. But yeah, the delta V of nearby equipment can turn on other equipment. What? Well, I want a Tesla coil that. What? The delta V. There's a field put out by the Tesla coil. It creates a delta V. And then everything inside the light bulb starts moving as if it's connected to a circuit where a delta V has just been applied. Not necessarily. No, the light bulb shouldn't have enough movement of charge for you to even notice. Because you're not directly touching it. You're not grounding it. You're just in the field. Your hair would probably stand up. Yeah. Your hair would probably stand up. You probably feel a tingle in the air. But as long as you don't get close enough to ground it. Okay. What was that meme video where the guy says turn it up and you hear zzz, and he hits the ground? You remember that? Oh, that guy got too close to the Tesla coil. He grounded it. It grounded through his brain. No, he's not dead. He was disoriented for a while. But you could if the Tesla coil was strong enough. Electrons are going to ground close to the speed of light. That's not, no. But would it? If it's strong enough, yes. Yeah, if you have a strong one, you don't want to pick it, you don't want to touch it, You can get small ones on Amazon. Get one that won't kill you and see what a small one does. If you get a small enough one, it shouldn't make you stupid at all. It's just going to feel like you got, I don't know, it's going to feel like you got hit with needles. So. This? Yeah. All right, so let's start thinking about how we can relate current to this new model. So an electric field is applied, a delta V is applied, current and electric field go in the same direction. The electric force on the electrons is pushing them in the opposite direction, and that's the direction of your drift velocity. So we're worried about the electrons that pass through a volume of that material in a time delta t. So the distance, or you can say x, the distance that they travel is the drift velocity delta t. So they're moving through a cylindrical volume. How do you get the volume of that cylinder? area of the circle times the length. So the area, the cross-sectional area of the wire, V delta T. Now, the total number of electrons moving through that volume, total number of charges, or you could say the amount of charge moving through there is going to be the number of particles multiplied by the volume. So that's like your total number of charges. It's the number of individual electrons multiplied by the volume. We also know total charge that moves through there so that tells us that the total charge that moves through the volume this is going to equal our current. Oops, sorry, I missed a delta T. Delta T, and then if I divide through, we get our relationship to current. So next time we'll solve a problem starting to use this. Don't forget